In this question, a block of mass small m placed on a horizontal conveyor belt is attached at one end of a spring of force constant K. The other end of the spring is attached to a support A. Coefficients of static friction, static and kinetic friction between the belt and the block are mu s and mu k, where mu s is greater than mu k. Initially, the belt, the block and the support all are moving towards right with constant velocity u, so all are moving and spring is relaxed. The support is suddenly stopped. We have to explain qualitatively the mechanism motion of the block after the support is stopped, and we have to find the maximum minimum deformation of the spring and the time period of the oscillatory motion of this block. So let's analyze the situation and solve for this maximum minimum deformations and time period. So just see what I am telling in this particular situation. So first we will analyze and then we will solve. So initially when this is just stopped, when support is just stopped, so this is the conveyor belt, and this conveyor belt is obviously, it is always moving with that constant velocity u, and at that particular instant, just after the support is stopped, at that particular instant this block is moving with velocity u, but this is stopped. So now this is the fixed end of the spring and this end of the spring is moving. So due to that, a spring will elongate, and due to elongation of a spring will exert force, a spring will start exerting force. Okay, so initially the spring force is 0 at this moment, and when it just moves slightly forward, slightly away from this natural length, so this dotted line represents the natural length of the spring. I will show the natural length using NL. So from this natural length, let's say this block is slightly away from this natural length. So if it is slightly away, so spring force will be very small, and if a spring force is very small and at this particular time there was no slipping between this belt and the block, so friction will come here because this spring force will tend to retard this block. So a spring force will oppose this friction force will oppose the tendency of sliding, okay, due to this spring force, and initially this friction will be static one. Okay, so this will be static friction, and this static friction will exactly balance this spring force. So initially these two forces will be balanced, and if these two forces will be balanced, so this block will still move with this velocity u. Net force on this block will be 0. So net force on the block is 0 and the block continues to move with velocity u. And in this process, obviously, so this spring force will increase because the extension, the spring will increase. So if a spring force increases, so it has to increase to oppose the increasing tendency of sliding due to this spring force. So it will increase, but there is a limit of static friction. So it will reach its limit. Until its limit reaches, spring force and this static friction force will balance each other, and it will continue, this block will continue to move with constant velocity u. So it will move with constant velocity u with these two forces balanced. Okay, now let's move further. So finally it will reach a position here. So it will reach a position here, and at this position the spring friction force will reach to its limiting value, and that limiting value here will be equal to mu s into normal, and normal is simply mg here. So till this point B, the motion of this block is with uniform velocity u. This all the forces will be balanced, these two forces will be balanced, and after this, okay, so let's see what happened after this, and this extension will be equal to mu s mg by k. Okay, so this is a natural length, and till this point the extension of the spring becomes mu s mg by k. Now it will move further, and it will move further, then spring force will further increase, and if a spring force increases, so but it cannot increase. Okay, so it has reached its limiting value. So now it will be converted, the friction force will be converted into kinetic friction force, because now sliding will start. So now this will be suddenly converted to the kinetic friction. So from B, we can assume that from B just to the right of B, it is now having kinetic friction. So kinetic friction will act from here, and spring force will continue to increase. So just I have written here So between this B and C, if you see the free body diagram of the block, so free body diagram block will be something like this. This is this kinetic friction here, and this is the spring force. So on this block now there are two forces. One is the constant kinetic friction force. This is the constant kinetic friction force, and this is the variable spring force. So we very well know that in a spring block system, if one force is constant force and other force is the spring force, so that system performs a simple harmonic motion. Okay, so this system will perform simple harmonic motion, and since this is only the variable force, this spring force is the only variable force, and that variable force is of the type k into x, so that is k into x type force. So if that is k into x type force and this is a constant force, so it will perform SM with this much angular frequency. Angular frequency is under root k by m here. So under k by m is the angular frequency of this SHM. So this block will perform SM from B to C. Okay, so from B to C, and C is the position where it will stop because it is continue. It will retard continuously because this spring force is more than this friction force. So it will continue retard and finally it will stop, and this will be the extreme position in this SHM. Okay, so this is the extreme position for this SHM. Next. So this is the extreme position for that SM. Here its velocity becomes 0, and as we have discussed that it is performing simple harmonic motion. And where is the mean position of that simple harmonic motion? So to find mean position, we will balance these two forces, spring force and the kinetic friction force we will balance. Okay, so wherever these two forces will balance each other, that will be the mean position for this particular SHM. Now forget about this constant velocity and all. Now we are concerned with this simple harmonic motion of this block. So equate this spring force with this mu k mg, which is the kinetic friction force, and you will get the extension in the spring when there is mean position. Okay, so at the mean position, what is the extension? And this position I am denoting by D. So this is D. So this is the mean position for that particular SHM. So this is the mean position, this is the extreme position. Okay, so extreme position and mean position, distance between these two positions is equal to the amplitude of this particular SHM. Okay, so this is the amplitude, and in this particular SHM, at this particular location we know the velocity because here it was moving with v velocity, as we have seen in this diagram. Here it was moving with this v velocity, this u velocity, which is the velocity of the belt also. So it was moving with u velocity, and you can assume that from here only the friction force is converted into mu k mg. Okay, so from V, mu k mg friction force starts acting on this block, and at this particular location velocity was equal to u. So in SHM we know that where is the mean position, we know that what is the velocity at some particular location. Okay, so we can use this formula. This formula is V is equal to omega under root a square minus x square, and from this formula we can calculate the amplitude because we don't know the amplitude. What is the amplitude? We don't know. So we know velocity at a particular displacement. X is displacement from the mean position. So this displacement is displacement from the mean position. So this is the mean position, and what is the displacement of this point from this mean position? So this is mu s mg by k minus mu k mg by k. So this is the displacement x here. Okay, so I can put this x value here. Omega is under root k by m. Velocity is equal to u at this location. So we can put all these values and I can find the amplitude. What is the amplitude of this motion? So amplitude will come out equal to this one. So this is the amplitude. Okay, so on calculation you will get this amplitude. So this is the amplitude for this particular motion. Now let's move ahead. So this is the extreme position, this is the mean position, D is the mean position, B was the position where the velocity was equal to u. And now in one part we have asked that extension the spring or deformation the spring. So this is the maximum deformation when it is at this extreme location. And what is this deformation? So this is the natural length, this is your amplitude. So in amplitude you have to add this value mu k mg by k. Mu k mg by k is what? This is the extension in the spring when it is at its mean position of SHM. It is the mean position of SHM, mu k mg by k. Okay, so remember this thing, this is the mean position of SHM. Okay, So where in that SHM forces acting are mu k mg and the spring force. Okay, so where these two forces are balanced, that is the mean position. So this is the extension of the spring when block is at its extreme position. Okay, so this is equal to this one, so mu k mg by k, and adding this amplitude. Now we have analyzed the motion till this point C. Now what after this? So after point C, now let's analyze the motion. So forces acting are this mu k mg, because there is slipping, so this force will continue to act, and this is spring force, and since the spring force is more than mu k mg, it will go in this direction towards left, and when it is going towards left, then spring force will continue to decrease, and mu k mg is a constant force, so again it will perform SHM, because this is a variable force and this is a constant force, so it will continue to perform the same SHM which it was performing from B to C. Okay, so the same SHM means the same angular frequency under root k by m, so it will go in this direction until it reaches this point. Spring force is always greater than this mu k mg, and this is the location where the forces are balanced. Okay, so this is the location where the forces are balanced, so this is the mean position. So let us show this on the next page. So this is the mean position, and when it reaches its mean position, this is the direction of velocity, and these two forces will be balanced, but due to velocity, obviously it will move further. Okay, it will move further and it will stop somewhere here, and we can very well calculate what is the position, because this is the extreme position, this is another extreme position, and we know the amplitude of this SHM. Okay, and this is the natural length of this spring. So this distance between mean and extreme, so mean and extreme, this distance is obviously the amplitude. Now I can calculate what is the deformation of the spring. So deformation of the spring is, again, this total is mu k mg by k, and from this I can subtract this amplitude. Okay, so this is the deformation, so this much is the deformation, and amplitude is the same as we have calculated earlier, because this is a simple harmonic motion in which this is a constant force. Okay, so it is the same kind of SHM. So mu k mg by k, this is the total distance, mu k mg by k, and minus this amplitude, so this is the amplitude, and amplitude we have calculated earlier, so from there we can find the deformation, and this is the minimum deformation in this particular motion, because this is the extreme. Now it will go in this direction again. Okay, so now let's analyze the motion after this point T, which is the extreme. So these are the two extremes, C is the right extreme and E is the left extreme of this SHM. So let's see what happens when it moves in this direction now. So it starts from the extreme position, because the friction force was more there at the extreme, and when it moves like this, so its speed is again increasing, because at extreme velocity was 0, and now it will move in this direction. So this is a location, I have marked a location called F, and we know that, and this is the mean position, and from mean position at a particular displacement, velocity was equal to u. So from the mean position on this side also, there will be a point at the same distance. This distance is mu s minus mu k mg by k, and this distance is again mu s minus mu k mg by k. So velocity is same. Okay, speed is same. Speed is u here, and here also the speed is z. Okay, so if speed is u here, so what will happen? The belt speed is also u, and this block speed is also u here. So now there will be no sliding. Okay, so there will be no sliding here. If there is no sliding here, so and here spring force is also less, so that spring force can be balanced by the static friction force, because static friction force will try to prevent sliding. Okay, try to prevent sliding between block and this belt, and spring force is also less. Spring force is also less here. Okay, because here the spring force will become equal to the kinetic friction force, and this is the location where extension is such that it is equal to the limiting friction force. So obviously the spring force is less, and it can be very well balanced by the static friction force, and this static friction force will be lower than the limiting friction force. Okay, there is no need of limiting friction force at this particular location. Limiting friction force will be required at this location. Okay, so this spring force and static friction force will balance each other here, and it will move with the constant velocity now. So now the SHM vanished, SHM गायब हो गया यहाँ से, अब SHM is not there, and it is moving with the constant velocity. When it is moving like this, again the deformation, the spring is increasing, spring force is increasing, and that can be balanced by this static friction force. It will adjust itself, it will increase, and it will balance this spring force. Now till when this balancing can be there, so this balancing can be there till this point B. Okay, so this point B is at a distance mu s mg by k from the natural length. Okay, so this is the same point B as we have discussed earlier. So at this point limiting friction starts acting. Okay, so from this F to B it will move with the constant velocity u, and after this, now the limiting, it has reached limiting friction force, so now it cannot increase further. So now we can see that it will repeat its motion now. Okay, so if we go back, okay, if we go back, then at B, at the location B, we have seen that at the location B the velocity was equal to u. Okay, at the location B velocity was equal to u, and it was going in this direction, and the forces were balanced. Okay, F limiting and spring force were balanced. Now we are at the same position now again. Okay, so this is the point B, again the same situation is happening, and after that the same kind of motion will be repeated. Okay, so after this there is no need to analyze, because the same kind of motion is again going to repeat. Okay, so now we can find the time period of the motion. We have analyzed the motion in complete one time period of this. So now let's calculate the time period of this motion. So I have drawn a line, and this is the mean position of that simple harmonic motion, and this is the same point B as we have discussed. So I am starting from this point B. So from point B, let's say this SM started, so it has gone till this point, and this is the extreme position, and then again it returned and it reached to this left extreme position, and from left extreme position it is again performing SHM till this point F, and between F to B this is not SM now. Between F to B this is not SM, this is motion with constant speed u. Okay, so this is a constant speed or constant velocity motion. So this red line in one complete time period is showing the motion with the constant speed, and this is showing the SHM. Okay, so now we can find the time period. So for finding time period, let's first find this time. Okay, so time taken in this uniform speed motion is, what is the distance by the speed. So distance is twice of mu s minus mu k mg by k, and divided by this speed. So let us call this as t1, and time taken during this SHM. Okay, so during this SHM, so for that I have drawn this circular motion projection method I am using. So this circle I have drawn, in that circle the angular frequency becomes the angular velocity, and this is the F and B point, and from this complete SHM motion we have to subtract this time. Okay, so suppose this is complete SHM, and complete SHM, suppose there was no uniform speed motion, it was doing completely SHM, then in that case the time period would have been 2 pi under root m by k. So now it is not 2 pi under root m by k. So what I will do is, the total time period for the simple harmonic motion, standard simple harmonic motion, is 2 pi under root m by k, and I can subtract this time. Okay, I can subtract this time, and instead of that I will add this time. Okay, so that will give me the time period. So for that I have to find this angle. So this angle is 2 theta, this angle is theta, and this angle is theta. This distance is mu s minus mu k mg by k, as I have written here. So I can find the sine theta, and theta is equal to omega t, and from theta is equal to omega t I can find the time. Okay, so this time, so theta is 2 theta here, 2 theta is equal to omega t, that will give me this time. Okay, I will subtract this time from the complete simple harmonic motion. So sine theta you can calculate from this diagram. So this is OF divided by this amplitude A. Amplitude A is, we have calculated earlier, this is equal to this, and in the answer given in the book they have used they have not used sine inverse theta, they have not used sine theta, they have used tan theta. Okay, so tan inverse of the angle they have used. So you can find the tan theta also from this diagram. If you find tan theta, so this is square minus this is square, so if you subtract this you will get tan theta. Tan theta is now this by this, so if you get tan theta, it will be equal to this one. So this is the value of tan theta. So what is the time period? Time period is simply that t1 with the uniform speed from f to b, and from this complete motion I will subtract this time. So complete motion will take 2 pi into m by k, and this is the angular displacement 2 theta divided by the angular velocity omega. Omega is simply under root k by m. Okay, so I will put it here, and theta you can put in terms of sine inverse or in terms of tan inverse, so whichever you like. Answer given in the book in terms of tan inverse. Okay, so this is it. This is the time period of this motion.